So we're going to start our study of linear water waves. So this models the water waves in, say, the ocean, or like a deep lake or deep river or something. This is pretty long. There's a lot in this video, or this series of videos. What I'm going to do is I'm going to break it up. We're going to do a little bit, and then I'm going to stop the video, and then I'm going to do the next bit, and that's going to be a separate video. So whilst this set of notes called linear water waves will continue to grow, it'll be across several videos. We need potential theory, so if you haven't watched the video on potential theory, go back and do that first. We're going to use potential theory and Laplace's equation and go from there. So the situation we're interested in is as follows. We have a bed, so a surface, it's flat despite my artistic ability, and that is some depth, that's the bottom of our ocean, for example. We're going to impose a coordinate y equals h upon this, so our little coordinate system is going to look like this. We're going to have y equals 0 at the mean of the top surface. So y x, we are going for 2D flow. I'll explain that in a second. But this here, this red dashed line, is going to be our y equals 0 line. We're going to consider a small wave. No, that was not a scribble. We're going to consider a small wave, and small in amplitude compared to the depth of the water. So we're going to have water in here. We're going to have air out here. This free surface is going to be wavy. We're going to set a reference pressure at sea level, at the mean, or the free surface, of 0. Okay. We have two things driving our wave motion, really. The inertia, so this flow has been set in motion. So we have perturbed our surface in some way and given it some wobbles. And gravity is the restoring force. Gravity is trying to pull the wave back into equilibrium. Okay, you can have waves of a similar form where the restoring force is surface tension, but what we're going to do here is think of it as gravitational. We're going to make some assumptions. We're dealing with water, so we're making the incompressible flow assumption. We're assuming that the flow is irrotational. Now, we get away with this assumption because these waves are quite big compared to the turbulence scale. So if you think about the ocean and waves in the ocean, and when we're talking the deep kind of ocean here, you've got a small perturbation on the surface, right? Like the wave height is small relative to the depth of the ocean, but the wave height is big relative to turbulent, swirly things, wind-driven ripples, and so on. So irrotational flow isn't too bad an assumption. Of course, irrotational, and incompressible mean that we have potential flow. Namely, that U can be described as the gradient of some function phi. I'm doing a lowercase phi here rather than the uppercase like that because the lowercase is easier to write and I'm going to be writing it a lot. We also have that the Laplacian of this quantity is 0. You know that from the potential theory video. We're going to assume that the flow is 2D. Now, that assumption just says something like this. If this is your, nice rectangular slice of the ocean, where you've got the seabed down there, and you got your clam, your seaweed, little fishy. Oh, they're weird fishies at the bottom of the ocean, aren't they? They're like those ones. That's your wave. You're assuming that wave is pretty wide, right? There's not a lot of change across, so you can say that not much span-wise variation. And your 2D approximation is reasonable, right? Because if you slice along that line, or you slice along, or you slice along that line, you're going to get pretty much the same picture. So we have a two-dimensional Laplace equation controlled by boundary conditions. So remember that the Laplace's equation is entirely driven by the boundary conditions. Because we're considering just a random old fluid, we've got to set these things. What we're going to do is we're going to assume that we have an impermeable fluid bed. So another assumption. Now, impermeable means that there's no flow into the bed. Now, in an ocean, you've got sand. The sand is wet. There is actually a flow into that bed. But let's say that magically we've got some nicely sealed concrete ocean floor. And we say that there is 0 velocity crossing this crossing the bed. We do not care if there is slip along the seafloor, right? We're going to assume that that can actually happen, right? So this is okay. This kind of means that we're not dealing with the usual no slip conditions that you would have for a viscous fluid. And if you like, you can consider this an inviscid flow. Not that that matters because we're actually just dealing with potential theory, which means we're just considering conservation of mass, which means the conservation of momentum and viscosity does not actually feature in our thinking. What we're going to do is say that there is no v velocity across this boundary. So v equals 0 when y equals -h. We have the definition of v from here. Recall that we only have two components because it's two-dimensional now. So our v is d phi dy, right? So you can see the rate of change of phi with respect to the vertical coordinate is 0 at the bed. So that's our first boundary condition. All right. The next boundary condition that we're going to have to think about, well, there's three more that we have to think about. We have to think about what's going on the free surface. We have to think about what's going on at these ends. Right, what's going on in X? X is easy. We're actually going to assume that the flow is unbounded in X. That is that X is defined like that. It's the whole real line, and we're going to say that the boundary is open. That is that it just carries on. Now, I guess sometimes we need a finitivity condition over these things. With a periodic function like a wave, like these wiggles that I've drawn in here, right? If they're like a sinusoid, they're defined everywhere on the real line, so we're actually okay. We're not going to blow up. We've got a bounded solution. And that's the only thing that we're going to technically demand. Make sure the solution is bounded. Now, bounded means that it is between two distinct finite limits. So our y velocity, the free surface y doesn't blow up, right? We don't have suddenly an infinitely tall wave, right? We have a wave that oscillates between height 1, or the maximum, and height 2, the minimum. Okay, so that's just in X, right? We've still got a boundary condition in Y to deal with. That is the free surface condition. So we've dealt with these boundaries. So these are unbounded coordinate, bounded solution. That looks like that, we assume. We have d phi dy equals nothing there. We need a free surface condition. Right, so free surface conditions are tricky to specify. What we're going to do is we're going to firstly define the coordinates. We're going to say that this free surface is equal to y, and we're going to call that eta x of t. That is the free surface. That is the height of this wave as we vary in both x and time. We're measuring from the 0 line, which is along here. And we're going to demand that this function eta has 0 mean. So when you integrate in time and space to take the mean of eta, the average value, you get 0. We're going to denote the average value by an overbar. Like so, right? And this is just the wave height, right? So the average perturbation that we're seeing is 0. So we're along there. And this y now is a function of x and t on that free surface, right? This is the free surface, the description of the free surface. Eta is an unknown function. All right. So we haven't made huge progress. We've done some of our boundary conditions. We would now like to figure out what that free surface looks like. Now, the information that we have is to do with the velocity potential, not with the shape of this surface. So let's say this is our surface, eta xt, right? And I guess you can draw a little coordinate system along here to illustrate this, and it can change in time as well. But when you're surrounding this, you actually have information about the velocities, right? So you have velocity information. U is this as a vector, and you have that as a function of x, y, and t, right? But on the free surface, y equals a function of x and t. Therefore, on the surface you have velocities are functions of x and t, right? Because you're stuck to this surface, right? So imagine you're stuck at that dot. You have a vertical component of velocity, which we call v, and we have a horizontal component of velocity, which we call u, and we have the resultant velocity, which we call u twiddle with the vector, right? So if this is your, if this is your wave at time t1, let's label this as t1, and you move to time t2, right, you do so with this velocity u under twiddle. So if I were to draw a new wave, right, something like that, this green dot there is, the coordinate is x at time 2, right, so this needs a time 1 as well. This is x at time 2, t at time 2, but the y position, the height, right, this is our x, the y position is eta of x2 t2, right? So I should write in that, let's write this red dot, let's just ditch this and add in another. This red dot is x1 eta x1 t1. Okay, so that's a bit more precise labeling, and then the blue line is just eta, the whole thing, and the red point is this now red label, the green point is the green label. All right. Now, if we assume that these changes in time are very small, we literally can draw straight lines in between them, right? We're going to assume that these perturbations are small. We're going to assume that the change between time 1 and time 2 is very small, and you can sort of see that you're going to get a delta t type thing, so you're going to get gradients, and then we're going to take limits to get those gradients into derivatives. The y coordinate at time 2 is eta x2 t2. That's just the name of it. But it's this point, eta x1 t1 plus the time difference, right? So we're literally doing a rise over run business here. We're taking the vertical change, so we're only interested in this way, but it's the change in time, the run, times the velocity, right? That gives us the rise. So we know that this is t2 minus t1, the time difference, and we can work out the height difference by multiplying that time difference by the velocity v, which we pretend we know. We haven't actually solved for v yet, but we're going to do so through Laplace's equation, and so relating eta to v at the moment is a useful thing to do. So this is the vertical speed of our wave, or our water surface. And this is the time interval. Okay. Now we just beat this until we get some derivatives. Oh, actually, I tell a lie. We work out the x coordinates. So x2 is equal to x1 plus t2 minus t1 times u. So it's the same reasoning in the x direction as for the y direction. We do not know x2, all right? We know it from here, but we don't know it in there. And so it's actually pretty useful to do a Taylor series expansion of this quantity to try and get it into known quantities. All right. So whilst we're Taylor expanding a multivariable function, we're only expanding in one of the directions. So the Taylor expansion is actually a single variable Taylor expansion. So it's the same ones you would have seen in first year, and it's very straightforward. So we get eta x2 t2 is approximately equal, or it's actually exactly equal. But I'm going to ditch all I'm going to make my approximation in the next step. x1 t2, right? The time doesn't change, right? We're not mucking around in time. d eta dx, these are partial derivatives because eta is a multivariate function, but this is evaluated at x1 t2, so it's only a single variable. The only change is an x, right? And we have to multiply this by x2 minus x1, then plus a whole bunch of other stuff. Higher order terms. I'm approximating this change by a straight line, right? This is a linear function. That's a gradient. That's a straight. This is otherwise a straight first order approximation. Or you can call it linear. So what we're now going to do is we're going to collect the rise and the run, if you like. So we have a couple of expressions for these things. We have this expression here. We've got this information here as well, and we've got our Taylor expansion. And when we put those things together, we get eta x1 t2 plus d eta x. So this is the Taylor series bit. Equals, this is the thing from the velocities bit. Note that now we've got a t1 here, and this is t2, plus t2 minus t1, v. Right, so this is our Taylor series, and this is our result from the y-coordinate here. And we've just substituted it for that. All right. We can now identify that this bit and this bit is like a change in time, right? It's the same x-coordinate, but different time coordinates. This is different time coordinates as well. And so if we think of this quantity, eta x1 t2 minus eta x1 t1, right? That is the rise of a function. This thing here, t2 minus t1, is the run. So you can see how we're getting to construct a derivative here, hopefully. So what we've got, you just take that over there, d eta dx. Oops, let me write this slightly differently. I'm going to write this up here, x2 minus x1. Then I'm going to write the derivative, dx x1 t2. Right. Now on this side, I actually have t2 minus t1 times v. I'm going to divide by t2 minus t1. Okay. And now what we've got is we've got essentially a gradient. This thing here is in the limit d eta dt. This thing in the limit is dx dt, right? So what we're going to do is we're going to let t2 tend to t1, right? Or t2 minus t1 tend to 0. And we're going to just take this limit. The limit of the v velocity is just v. This thing becomes d eta dt. This thing becomes dx dt. This thing doesn't change. And we're left with the following. Oh, this does change because we're taking the limit. So that's d eta dt. The interesting thing is that the change in x with respect to t is the u velocity. Right, so that's the change in x position with respect to time. That's u. So d eta dx. This is now x1 t1, and I could write that in if I wished. I'm not actually going to because it's irrelevant, because this is at the same coordinate. All of the arguments no longer matter, right? I'm no longer tracking the arguments because I've taken those limits and I'm all at the same point again. So I'm just going to write d eta dx equals v. right? This, interestingly, is valid on the free surface. We have to remember that all of this, we've glued ourselves to the surface. Y equals eta xt. Again, the discrete coordinates, x1, x2, doesn't matter. This is valid for all of them because we took that limit. This thing here is called the kinematic condition for our free surface. It's an expression that relates the shape of our free surface to our fluid velocities, and remember, our fluid velocities are related to our velocity potential. Right, so this tells us the shape of eta in terms of the velocities, but we don't understand any of the forcing that we've done, right? We don't know how this thing is in motion. We've only just pretended that we've got some velocities u and v. We don't care how those u and v arise. So that's why this is called the kinematic condition. Kinematics is the study of motion where you don't care about forces. So it's called the kinematic condition, and it describes the free surface. The next video will be where we look at the dynamic condition, where we need Navier-Stokes and Bernoulli, and we need to make some more approximations, but we'll get another expression on the free surface that helps us close out this problem.